All right. In this video, we are going to be talking about the tangent line problem and the formal definition of the derivative. Back in Unit 1, we talked about limits, and that was all fun and games. Now in this unit, we are going to be talking about the tangent line problem, and essentially, we know that a tangent line touches a curve at one point. It's easy for a circle because it's just going to be perpendicular to the radius. That's easy peasy lemon squeezy. But let's say, how about a parabola that's not a maximum? So let's say this point right here. How can we draw a tangent line at that point? Or a tangent line at this point? Or a tangent line at this point right here? It's kind of hard for us to draw a tangent line and find the equation for it. But what we are going to be doing is using a secant line. And essentially with our secant line right here, what we're going to do is as we approach my point that I want to find the tangent of, my secant line right here in green, as I move this right here and move it closer and closer and closer and closer, you'll notice that my green secant line is eventually going to become my blue tangent line. So now our goal is to figure out how can I write this equation based off of these 2 points. Well, if I have c and f of c and I have x and f of x, I could write the secant line by saying f of x minus f of c all over x minus c. That's my secant line, which was in green. Now, my tangent line here, as I get closer and closer and closer and closer and closer, what I can do is write the tangent line in terms of the secant line by taking the limit. So here, as the limit approaches c of my secant line, this right here will eventually become my tangent line at point c f of c. So once again, as I get closer and closer and closer and closer to my, let's pick another, let's do this. So let's pick another point, and as I get closer and closer and closer and closer to it, I'm eventually going to have to take a limit, and we want to be very close so that it eventually matches up to my secant line. All right, so essentially the slope of the tangent line is going to be our derivative, provided that the limit exists. So we have 2 concepts for us. We have the tangent line, which is going to be the derivative, and we'll have 2 formulas. So this formula is my derivative of a function. So the limit as x approaches 0 of my quotient, difference quotient that we did in the previous video. And then this one right here is going to be my derivative at a point, aka the slope at a point. So we're going to be using these 2 formulas today. The derivative can also be used to determine the instantaneous rate of change. And of course, the process of finding the derivative is called differentiation. We are going to have several types of different notations that you guys will need to know. The first one is this right here. This is f prime of x. F prime of x. We also have dy dx. And then we also have y prime. So these right here are going to be your 3 big formal notations for the derivative. All right, so number 1 says go back to the first page of the packet, and then we're going to find the derivative of the functions using the limit definition. So we've already found the difference quotient already, and what we're going to do is just take the limit as h approaches 0 for these 3 functions right here. So here, if we take the limit of this right here as h approaches 0, well, remember that my difference quotient was just 2, So here, my limit, or my derivative here, is just going to be 2. So this means that f prime of x is just 2. Here, if I take the limit as h approaches 0, this is just going to be 0. So now I have 2x plus 1 as my derivative. Right now, it probably doesn't make sense because it's a function. However, we are going to go back to number 2, number 3, and think about why this works in terms of a point. And then for this one, if I were to take the limit as h approaches 0 of my difference quotient, which I forgot to write, this right here is going to be, that gets canceled out, It's just going to be 3x plus 2. This is my derivative, 3x squared plus 2. I forgot this right here. Oops. All right. For number 2, I'm going to do this 2 ways. I'm going to do it using this notation here, and then I'm also going to do it with this notation here. Given that you're given a point, it's going to be much easier if you do this version whenever you are finding the derivative at a point, aka the slope at a point. This one right here, don't use it unless it really asks you to find the derivative of the function, which would do in number 4. But for number 2, it says find the slope of the tangent line to the graph of f of x is equal to x squared at the point -2, 4. And then we're going to be using the slope to find an equation of the tangent line at that point. And then we're going to estimate what f of -2.1 is using the equation. All right, so first I'm going to go ahead and do this notation right here. This is going to be my difference quotient. So what I'm going to do is go ahead and do the limit as h approaches 0 of x plus h squared minus x squared all over h. Then I'm going to do the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. Notice how the x squares cancels out. And then the h's right here, I could also simplify them. So now I just have the limit as h approaches 0 of 2x plus h. And then if I were to plug in h, I'm just going to get my function of 2x. Excuse me. So this tells me that the derivative of x squared is going to be 2x. Now at the point -2, I'm going to plug in -2, and this tells me that the slope of the tangent line at -2 is going to be 2 times -2, or -4. So here, if I were to draw the slope or the tangent line at the point -2, 4, I'm going to have a slope of -4. 1, 2, 3, 4. 2, 3. 1, 2, 3, 4. And then I'm just going to go ahead and graph it like that. That's not pretty. Graph it like that. So there's my tangent line. Now we have the tangent line. What I need to find is the equation, and then equation of the tangent line, and then estimate f of -2.1. Well, remember that in order to make an equation, I need 2 things. I need a slope, which I already have, and I need a point. In this case, I'm going to be using what they give us, -2, 4. So now I'm going to use my point slope formula. Y minus 4 is equal to -4, x plus 2. And then I'm just going to plug in -2.1, and then call it a day. Now, using my handy dandy calculator, I'm going to get 4.4 as my estimate. So this right here is my estimate of f of negative 2.1. Now, if I were to actually find out what f of negative 2.1 is using my real equation of x squared, that's going to be 4.41. So we were off by 0.01. Now, because we were off by 0.01, this right here is going to be called an underestimate. This is an underestimate. An underestimate essentially just means that our guesstimation right here was less than what our true actual value is. You'll also notice that my tangent line right here is below my curve. So this is another way to say that, hey, this is an underestimate because my tangent line is below the curve. Now, like I said, this was me using my first definition right here, my difference quotient. What I'm going to do, which is going to be very easier now, is the derivative definition at a point. So I'm going to be using this definition now with number 2. And we're going to see how that's going to be much easier because you have a point instead of doing all this mumbo jumbo right here. Because this right here was a mess. All right, so we're going to be doing the same thing. I have the limit as x approaches c. C is going to be the value that we have. So this, in this case, it's going to be negative 2. I have f of x, which is x squared. I have my value of c, f of c, which is going to be 4. And then I have x minus c, so x minus negative 2 or x plus 2. Now, direct substitution isn't going to work, so I'm going to go ahead and factor this out and then cancel out the x plus 2. If I do that, now I'm just left with the limit as x approaches negative 2 of x minus 2, which is going to give me negative 4. And that is my slope at the point negative 2, 4. And see how we only did like a couple of steps. So that's why I would encourage you, if possible, to do the definition of the derivative at a point using this limit right here instead of this one right here. So this one point, this one function. Then, of course, the same thing. We know that we have a slope and a point, so that's going to give us this. And then, once again, it's going to give us an underestimate. All right, we're going to do number 3. This time, I'm going to be using the derivative definition at a point instead of this right here, because we don't like this. We hate this one. Okay, so we have the limit as as x approaches c of f of x minus f of c over x minus c. And remember that this was my secant line. Okay, so now I have the limit as x approaches negative 1 of x squared plus 1 minus 2, because f of c is 2, all over x plus 1. You'll see that I have the limit as x approaches negative 1 of x squared minus 1 over x plus 1. Of course, I could factor that out. X plus 1, x minus 1, all over x plus 1. Don't drop the limit. Cancel that out. So now I have the limit as x approaches negative 1 of x minus 1, which is going to give me negative 2. Wow. Crazy. So I have a slope of negative 2 at the point negative 1, 2. Then, of course, I'm just going to go ahead and graph this. And call it a day. Then there's my tangent line. All right, so here I want the equation of the tangent line, and if you were to notice that here, it passes through the origin, so my equation is just y is equal to negative 2x. Surprise. Now, if I were to estimate f of negative 1.9, I'm going to plug in negative 1.9, and that's going to give me 3.8. Now, my actual value of f of negative 1, if I were to plug this in, is oh wait, f of negative 2, sorry. F of negative 2, no, f of negative 1.9 is 4.61. So once again, this is an underestimate because my guesstimation is less than my real actual value. All right, we will do number 4, and then I'll probably let you guys do 5 on your own. Number 4 says use the limit definition to find the derivative of f of x is equal to 4 over square root of x. So for this one, because we aren't finding the derivative at a point and we're finding the derivative of the whole function, we do have to use our lovely difference quotient formula here. So we have the limit as h approaches 0 of f of x plus h minus f of x all over h. So I have h approaching 0 of 4 over the square root of x plus h minus 4 over the square root of x all over h. And what we're going to do is go ahead and make the numerator one fraction. Then I'm going to same change flip it so that it's easy for me. All right, now we have radicals in the numerator. So we are going to multiply by the conjugate. I am going to be multiplying by the square root of x plus the square root of x plus h. We can really ignore the 4 because I can factor out the 4. So then I have the limit as h approaches 0 of 4 and then x minus h all over square root of x plus h times x times h times the square root of x plus the square root of x plus h. The denominator is very, very, very messy right now, but that's okay. We'll fix that. What I'm going to do is simplify the numerator, though, because that can be rewritten as negative 4h, because the x's will cancel out, and then I have a negative h right here. So that's going to be a negative 4h. You'll also notice that the h's will cancel out, so I'm going to cancel that out, which means I'm only left with a negative 4 on the top. Great. All right. Once we do that, I'm going to use direct substitution with h. So now if I do direct substitution, I get negative 4, the square root of x squared times the square root of x plus the square root of x. And if I were to simplify that, I'm going to get negative 4 over x. And then I have 2 root x right here. And then if I simplify that, I'm going to get negative 2x root x. So using our formal definition of the derivative, this tells me that my derivative of this lovely thing right here is negative 2 over x times the square root of x. Later on, we'll probably revisit this problem using the power rule. That once we get to the power rule, we won't have to do any of this mess right here because obviously this is very messy. There's also one thing that we didn't really talk about, which was an overestimate, which is actually what number 5 was going to be, because here your tangent line was going to look something like this right here, where it's above the graph. So an overestimate is an estimate that is greater than the actual value. And of course, like I said, the tangent line is going to be above the point slash the graph. All right, in the next video, we will talk about sketching derivatives and how to sketch them.